Good morning, everyone. I am Shanchari Karati from CSE department. First, I want to thank you for joining us today. We are excited to present our extensive research and insights on a significant topic: application of artificial intelligence in nuclear reaction and nuclear pollution control. Our main reason to choose this topic is that at the point of time, we must save our natural resources, mainly carbon resources. Secondly, in previous wars, we have noticed an active usage of nuclear energy, where radiation had caused potential damage to livelihood. We need to stop this at an early age to stop any further harm caused by the radiation. These factors provoked us to choose this as a topic for our presentation. Now, allow me to introduce my teammates Mrigangana Sarkar and Prerana Maitri from CSE department. Here, a brief overview of what we will cover in our presentation. Introduction.
What is nuclear energy? Importance of nuclear energy. History about nuclear energy. Basic terms related to it. Application of nuclear energy. Some merits and demerits of nuclear energy. Relation of AI with nuclear energy. Where is AI used in nuclear energy? Mechanism of nuclear energy generation and pollution control by artificial intelligence. Comparison of nuclear energy generation and pollution control with and without AI. Use of AI in nuclear science, and conclusion, videography and technology.
So, what is nuclear energy? Nuclear energy is a powerful and efficient form of energy generated by harnessing the process of nuclear fission, where the nucleus of an atom splits, releasing a tremendous amount of heat energy. This heat then used to generate the electricity, making nuclear energy a significant and low carbon source of power with the potential to meet the world's growing energy demands while reducing the greenhouse gas emissions. Now let's watch a video of how nuclear fuel is produced to generate nuclear energy.
Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction.
Now, we will discuss the importance of nuclear energy. Nuclear energy holds paramount importance in today's world for several compelling reasons. Firstly, it is highly efficient and reliable source of electricity generation, capable of providing a consistent supply of power, unlike some intermittent renewable sources. This reliability ensures the stability of energy grids and helps meet the increasing global energy demand. Secondly, nuclear energy is environmentally friendly, as it produces minimal greenhouse gas emission during electricity generation, contributing to efforts to combat climate change. As the world strives for a sustainable and low-carbon energy future, nuclear power stands as a crucial pillar for achieving these goals. As you can see, nuclear power has cut
Carbon dioxide emission by over 60 gigatons in 15 years, equivalent to nearly 2 years of global energy-related emissions. It now ranks second in low carbon energy sources.
Now, let's see a video for better understanding how safer nuclear energy can be.
So for the first time ever, I want to show you the world's newest nuclear power plants. Welcome to the Emirates. It's a country in the Middle East that is building nukes, not for war, but for peace. So they built this nuclear power plant that can power 25% of the country without any carbon emission. Because something as small as this uranium can power an entire house for a year. The best part about nuclear energy, it's 100% safe, 250 times safer than big oil fields. The reactor is very small. The walls are 1.2 meters thick. and every operation is tested 25,000 times. This is the newest and safest nuclear power plant in the world. From wind to solar to nuclear. I am excited because the future is going to be green. That's 1 minute. See you tomorrow.
Now, as you can see, the first chart, figure 1, includes the distribution of nuclear energy production in various countries of the world. 23% in USA, 13% in France, and 40% all others. In the second figure, the proportion of nuclear energy used among all the other energy sources in the world is presented. Now, to understand the significance of nuclear energy in today's world, let's journey back in the time to explore its fascinating history. In 1896, discovery of radioactivity took place. Discovery of artificial radioactivity took place in 1934. One of the most important things, fission, was discovered in 1938. In 1945, the French Atomic Energy Commission was founded. After that, construction of 2 nuclear reactors on the Mark IV site took place in 1955. After a short gap of time, Orano was created in 2001. Then creation of Orano took place in 2009. And finally, in 2021, rising energy prices in the EU, nuclear power established itself a competitive, continuous and low carbon energy sources. Now I will explain the basic terms of nuclear energy. I hope you guys are quite familiar with these terms: nucleus, atom, proton, neutron and electron. Now, atoms of the same element with different numbers of neutrons leading to different atomic masses are known as isotopes. The spontaneous emission of radiation from the nucleus of an unstable atom is known as radioactivity. The time it takes for half of the atom in a radioactive substance to decay is known as half time. A type of ionizing radiation consisting of 2 protons and 2 neutrons emitted during certain types of radioactive decay is known as alpha particle. A type of ionizing radiation consisting of electrons or positrons emitted during radioactive decay is known as beta particle. High energy electromagnetic radiation emitted from the nucleus during radioactive decay is known as gamma ray. The splitting of an atomic nucleus into 2 smaller nuclei, releasing a large amount of energy, is known as fission. The process of combining 2 light atomic nuclei to form a heavier nucleus, releasing a tremendous amount of energy, is known as fusion. A self-sustaining series of nuclear fission reactions producing a significant energy is known as chain reaction. And the minimum amount of fission material required to sustain a nuclear chain reaction is known as critical mass. Now I would like to call my teammate Prerana Maiti to continue the further discussion. Now, I would continue with the topic mechanism of nuclear energy generation. The mechanism behind nuclear energy generation is a marvel of science and engineering. Basically, nuclear energy is generated through 2 processes. One is nuclear fusion and another is nuclear fission. Nuclear fusion is a process where 2 atomic nuclei combine to form a heavy nucleus, and it releases an abundant amount of energy, and this energy is used for generation of electricity. Scientists are working on developing controlled fusion reaction to produce practical energy with the projects like ITER, International Thermonuclear Experimental Reactors, aiming to explain the viability of nuclear fusion as a sustainable energy source. Now, we will watch a video related to the mechanism of nuclear fusion.
For example, lighter nuclei such as lithium and helium, when combined together, form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is phrased in terms of energy release, which is usually very enormous rather than mass. Therefore, the law of conservation of energy is satisfied. Consider the example of 2 hydrogen nuclei combined to form deuterium. Here, 1 hydrogen atom combines with another hydrogen atom, giving deuterium, 1 positron and 1 neutrino. This deuterium, in turn, combines with another hydrogen nucleus to form a helium isotope. If two such helium isotopes are fused together, the formation of heavier helium takes place. These three steps of the nuclear process, where four protons are fused together to form the heavier helium-4 nucleus and an enormous amount of energy, is a nuclear fusion reaction. The chemical equation for this nuclear fusion is as follows. Four hydrogen nuclei, when fused together, give rise to the heavier helium. But how is this enormous amount of energy being liberated from such a seemingly simple nuclear reaction? To understand this, let's first calculate the loss of mass in the process. The starting mass of the four protons is 4 times 1.0078.
Now, the other process is nuclear fission. Nuclear fission is the process where the nucleus of an atom is split into two or more nuclei, releasing appropriate amount of energy.
Isotopes of the
This energy is used in generation of electricity. A few examples of nuclear reactors that carry out nuclear fission are light water reactor, which are most commonly used, and secondly, pressurized heavy water reactors. One of the examples of pressurized heavy water reactor is situated in Canada, the deuterium-uranium reactor, and the other reactors are molten salt reactors and heavy temperature gas-cooled reactors. Now let's watch a video how nuclear fission reaction occurs.
isotopes of uranium, like U-235, is hit by a particle, usually a neutron, then it will be split into two smaller nuclei. This is called nuclear fission. If the total mass of the two smaller nuclei is less than that of the uranium before it was hit, the missing mass is turned into energy via the equation E equals mc squared. In the case of certain isotopes of uranium and plutonium, such as U-235 and plutonium-239, when these are hit by a neutron, they split into two lower mass nuclei, and three neutrons are also thrown out. If there's enough fissionable nuclei in high enough concentrations, then it is possible for the three thrown out neutrons to in turn fission three more nuclei, which in turn fission 9 more nuclei, which in turn fission 27 more nuclei. You create what's called a chain reaction. This is the mechanism behind the atomic bombs dropped at Hiroshima and Nagasaki during World War II.
Now moving to the next slide, application of nuclear energy. Here is a graph that depicts the nuclear power generation till 2022. One of the applications of nuclear energy is in hydrogen production. Nuclear reactors generate high temperature heat which can split water into hydrogen and oxygen, and this hydrogen can be used by the industries like petroleum refining industry, chemical manufacturing industry, and sheeting metals, etc. Next is seawater desalination. In this method, heat generated by a nuclear reactor is used to evaporate seawater, and the vapor evaporates, and this vapor is then again condensed and back to a fresh water. Nuclear energy is used to provide the required high pressure stew for reverse osmosis. Thus, we can access more and more clean and fresh water in the regions having water scarcity. For example, the Russia has BN-G50 nuclear reactor in Kazakhstan, which is used for both electricity generation and desalination. Next application is district and process heat. Here also nuclear energy is used to produce high temperature, which is distributed through insulated pipes and provide heat in keeping multiple buildings for domestic uses and other industrial uses. This process ensures safety and efficiency while reducing the greenhouse gas emissions. For example, the Bor-60 reactor in Obninsk of Russia was connected to a district heating system in the city in 1960s. This heat is used for tasks such as brewing, laundry, drying, and sterilizing or melting materials. And now next is synthetic fuels and chemicals. Here, nuclear energy can help to produce nuclear fuels through nuclear transmutation. This process is used in the production of medical isotopes such as technetium, which is widely used in radiation therapy and for cancer treatment. Next is cooling and refrigeration application. This application using nuclear energy are relatively less common compared to the uses mentioned before. The heat from the nuclear reactor is used by the absorption cycle, which cools a working fluid that is ammonia or lithium bromide, and this fluid is then used for cooling purposes. Some industries like food processing industry and chemical manufacturing industries require large scale of refrigeration for storage and manufacturing products. So here nuclear energy can be used to generate the necessary fluids. Now, advantages of nuclear energy. Firstly, carbon-free electricity. Nuclear power produces minimal amount of greenhouse gas emissions, making it a low-carbon energy source. Secondly, small land footprints. Nuclear power plants require less land compared to some renewable energy installations. And thirdly, high power output. Nuclear fuel contains a high energy content, which is the main reason behind consistent power generation. Lastly, reliable energy source. Nuclear plants provide a stable and continuous supply of electricity, reducing the energy supply disruption. Next, coming to the disadvantages of nuclear energy. Firstly, dependency on uranium with finite global reserves may drive up to depleting the Earth's uranium resources, and more mining and processing of uranium may lead to negative impact on the environment. Secondly, construction and maintenance of nuclear power plants are expensive. Thirdly, nuclear power plants produces long-lived radioactive waste that requires secure disposal. So different countries with their respective governments are securing the disposal of radioactive waste without causing any disaster. Lastly, malfunctioning of the nuclear reactors. The hot radioactive vapors from the reactors may escape and release harmful radioactive materials into the environment. Another malfunctioning of reactors can be poor damage of the reactors. All these can be harmful for the environment and human health also. Now, I would hand it to Mrigangana for continuing with the discussion.
Thank you, Prerana. Now I will continue with the rest of the presentation. So, relation of AI with nuclear energy.
And cities.
So, firstly, AI can play a significant role in improving nuclear reactor design by simulation and modeling, by testing of various design parameters and safety scenarios, and also identifying and developing new materials that are more resilient and efficient for nuclear reactors. Next, where is AI used in nuclear energy? So it is used mainly in the three fields: nuclear science and research, nuclear power, and nuclear security and radiation protection. So firstly, coming to nuclear science and fusion research. AI is vital in nuclear science, aiding data analysis, research acceleration, and innovation. Fusion research in particular benefits from AI's problem-solving capabilities, enhancing experiment and simulations. Next, coming to nuclear power. Nuclear power, a dependable low-carbon energy source, can be enhanced by AI. Combining digital simulations with AI can optimize operations, improve reactor design, and boost efficiency, lowering maintenance expenses. Next, turning to nuclear security and radiation protection. AI strengthens nuclear security and safety by enhancing radiation detection, improving intrusion detection, and spotting cyber threat. It also reinforces radiation protection for workers in various fields like medicine, constructions, etc. Now coming to how AI helps in nuclear fusion. Nuclear fusion is a process which releases vast amount of energy, has been touted as a potentially limitless source of clean energy. But a number of technical challenges are still need to be overcome. Here on Earth, scientists use tokamaks, downward-shaped vessels surrounded by electromagnetic coils to try to create nuclear fusion reactions that occurs in outer space. The magnets in these tokamaks are used to contain the volatile hydrogen plasma, which is hotter than the core of the sun. Controlling the magnetic coil currently requires multiple layers of complex control system. These magnetic fields are essential for keeping the plasma generated by the reactor safely contained. If the plasma touches the walls of the reactor, it rapidly cools, stifling the reaction and potentially causing significant damage. Researchers at TCB previously used 19 magnetic coils, each controlled by a separate algorithm that monitored the interior of the reactors thousands of times a second with a host of sensors. DeepMind SP created a single neural network to control all the coils at once, automatically learning which voltages needed to be supplied to them to best contain the plasma. The team trained the AI on a precise digital simulation of the reactor before conducting experiments on the real machine. Ultimately, it was able to successfully contain the plasma for 2 seconds, which is approaching the limits of the reactor. TCB can only sustain the plasma in a single experiment for up to 3 seconds, after which it needs 15 minutes to cool down. Together with the Swiss Plasma Center at EPFL, a university in Lausanne, Switzerland, DeepMind says it has developed reinforcement learning AI system that can control the magnet and change their voltages thousands of times per second. Reinforcement learning is an AI training technique that involves programming an AI to take certain actions in order to maximize its chance of earning a reward in a particular situation. As well as controlling the plasma, the AI was able to shape it and move it around the reactor. New plasma shapes may bring efficiency or stability improvement in new fusion reactors such as ITER, which is currently being built in France and will be the world's largest tokamak when complete in 2025. The AI even demonstrated the ability to control 2 separate beams of plasma at once. Now I shall see a small video relating to this mechanism.
Intelligence drives nuclear fusion reactor. In order to better understand how plasma behaves, nuclear fusion experts have created a machine learning model that can automatically detect and keep track of plasma blobs that form inside of a nuclear fusion reactor around the tokamak. In the simplest terms, a nuclear fusion works by fusing together atomic nuclei in order to release energy, which is the same mechanism that fuels our solar system's sun and the stars throughout the universe. Because of the numerous advantages that fusion energy creation could have, scientists have been attempting to harness the energy produced by fusion reactors for many years. Some of these advantages include the fact that fusion reactions are clean and don't generate a lot of radioactive waste or greenhouse gases. Also, the hydrogen isotopes that power them are plentiful, so they also emit absolutely enormous amounts of energy. However, fusion reactions require extremely high temperatures and pressures, which consumes a lot of electricity. Therefore, it hasn't been possible for scientists to make a nuclear fusion reactor create more energy than it requires to operate, causing fusion reactions to be challenging to maintain over time. Using the tokamak, which is a donut-shaped device that employs strong magnets to circulate superheated materials called plasma around in a circle, is the most popular method of achieving fusion. Fusion takes place because of the conditions that this plasma produces. Near its edges, plasma frequently develops turbulent regions known as blobs by scientists. Monitoring the formation and movement of these blobs is crucial because they determine how heat and particles from the plasma interact with the inside of the tokamak. As a result, this helps scientists understand how the tokamak should be built. To protect the reactor and to make sure that the plasma reaction remains hot and stable, the plasma should be kept away from the reactor walls. In areas where major plasma wall interaction needs to be minimized, plasma blobs can convey significant volumes of particles and heat away from the main plasma.
Now, here is an example of use of AI in nuclear fusion. Presently, it has been used to confirm the plasma inside the TCB fusion reactor in Switzerland. Now, coming to mechanism of nuclear pollution control. So, to start with, here is radiation monitoring. In radiation monitoring, the monitoring system is carried out using a multi-sensor network which is designed to monitor radioactive materials in a large nuclear facility. Additionally, an artificial intelligence-based localization algorithm was developed to accurately locate radioactive materials. Next, coming to predictive modeling. AI has considerable analytical and predictive potential to help monitor power plant processes and detect anomalies. Next, coming to robotic cleanup. Researchers reporting in SCS Nano have developed tiny self-propelled robots that remove radioactive uranium from simulated water. Next, coming to image analysis. So AI can analyze satellite images and aerial photographs to identify areas affected by nuclear pollution and track changes over time. Now we should see a short video on image analysis.
The Route Offerable Unmanned Navigation of Drones, or RAND, will allow the autonomous operation of drones in known environments. ROUNDS was developed by the Department of Energy Light Water Reactor Sustainability Program to help automate activities of the current fleet of U.S. nuclear power plants. Cost and safety concerns have motivated the program to search for alternatives to plant workers performing routine activities, such as monitoring equipment or collecting readings. ROUNDS allows a drone to automate these manual processes, collect the same information at a much higher frequency, and reduce human exposure to hazards. Industrial environments often have obstacles that can be navigated by drones only as they are equipped with the means to quickly recognize and react to the environment. Other technologies that rely on environmental mapping are not as fast and precise as ROUND. They are also more expensive and require additional sensors, which add weight and consume more power. ROUND enables the drone to autonomously, accurately, and quickly navigate its environment and return to its charging location within a known area, covering a long route on a drone's limited battery charge, and preventing the need for charging stops along the drone's flight path. The novelty of this technology lies in ROUND's ability to read QR codes at any angle and reverse calculate its position. ROUNDS can then tightly control the drone's motion through high-performance controllers, such as those used to control missiles and satellites. By leveraging the drone camera and printed QR code stickers, the cost to deploy ROUNDS remains low. ROUNDS can be used in industries that perform security and operations route, warehouse surveys, and chemical or radiation monitoring in hazardous areas, among others. For further information, please.
Now coming to the next point, data fusion. AI can integrate data from multiple sources such as weather forecast and pollutant dispersion models to provide accurate real-time pollution assessment. Now coming to the next part, decision support system. AI-driven system can assist in making informed decisions by analyzing complex data sets and suggesting optimal pollution control strategies. Second, coming to emergency response. AI can assist in coordinating emergency responses by predicting potential pollution spread, evacuation, and resource allocation. Now coming to a difference, merits and demerits of AI in nuclear science.
Coming to merits of AI in nuclear science, firstly there is enhanced reactor safety by accident prediction, optimizes reactor operations for efficiency. Thirdly, it predicts and prevents potential reactor accidents. Fourthly, it simulates nuclear reactors for research. And fifth is it speeds up data analysis and pattern recovery. And the demerits can be vulnerability to cyber attacks and compromise of safety. Secondly, reduces human expertise and understanding. Thirdly, over-reliance on AI might lead to system failures. Fourthly, lack of transparency in AI decision making. And fifth is ethical concerns in AI applications.
Next, coming to another difference, that nuclear energy with using AI and without using AI. So first coming to nuclear energy using AI. High efficiency and output, ensure safety monitoring. Thirdly, it provides AI-assisted waste disposal. Fourthly, precise emissions monitoring. Fifth is AI-based risk analysis. Sixth is real-time adjustment. Seventh is reduced human intervention. Eighth is potential reduction. And ninth is potentially higher investment. If we consider nuclear energy only without AI, then the following point come into consideration. Consistent energy production, standard safety protocols, traditional methods of waste management, it takes conventional pollution control, conventional risk assessment, manual adjustment, standard human involvement, similar environmental impact, and standard operational cost. Now, to conclude, I would like to say that this nuclear energy project represents a pivotal step towards a sustainable energy landscape. Its potential to generate abundant, reliable power with minimal greenhouse gas emissions cannot be overstated. As we move forward, it is imperative that we prioritize safety, innovation, and responsible waste management to harness the full benefits of nuclear energy. Now, here are some of the references from where we selected our data. And finally, I would like to thank Sir Shomodji Khare for giving us an opportunity to present it. And I would also like to thank my friend Prerona and Swanchari for helping me to complete the entire presentation. Thank you so much.